And first of all, I don't see Gleb here. So I would like to thank him. Okay. Now we are ready. Maybe, I mean, my talk probably will be shorter than the schedule, so maybe if there are 20 seconds more to wait, I don't worry. Okay. So yes, good afternoon again, and thank you very much for asking me to participate into this workshop. Especially thanks to Gleb Kutuzov for his work and for remembering about me. And all right, so I, in fact, also have to apologize because I changed the title of my presentation, but I changed the title since I started seeing what was more or less the focus of this meeting. And therefore, I'm going to show something which is more related to spin chain rather than what I would have showed, what I claimed in my abstract. And yes, so my talk will be the last one dealing with fishnet integrals, fishnet theories, and but more from a spin chain point of view, as you can read from my subtitle. And what to say? Yes, I think it will present a primer of some interesting computation, but if time is left over, it cannot transform into a more formal, not that informal, but still quite informal discussion about fishnet theories, since there were many questions around. You can target me. All right, so let me start. Triangulation of fishnet diagrams. This talk is based on a series of works which were inspired by papers by Derkachov, Manashov, Korchemsky in the first step, and deal with spin chain with non-compact spin chain in infinite dimensional representations. So basically, the idea of my talk is use spin chain to compute Feynman integrals. Feynman integrals, Feynman diagrams are the objects that describe the perturbative expansion in the coupling in quantum field theories. Since not everybody here works with the physics or with the quantum field theory. Okay, so we want to apply spin chain to Feynman diagrams in conformal field theory. So we use some tools that Sergei taught me, and we have a series of papers where we work out this method. My talk will insist mostly on this on results in these two single-authored papers. This is not out yet, so it's a strong claim to have it, and also will point towards some application. But really, the roots are in the work by Grisha Korchemsky, Sergei Derkachov, and Alexander Manashov. Also, I will cite from time to time some results. For example, I could refer in the end to Loom CFTs that Volodya explained, or Kazakov explained to you, or generalization of the present computation that are related to these other works. Okay? Because as Volodya told you, these fishnet theories are pretty easy to generalize, either in more or less space-time dimensions, or changing the type of interaction, adding interaction, and developing different structure of your Feynman interest, as in the Loom. One can play around a lot, but with theories that are all they are all featured by integrability, which is based on star triangle relation. And here I would already put a question somehow myself to the audience or the experts, how to write down a theory which is still described in terms of simple Feynman diagrams as the one that Volodya explained, but not based on some on star triangle relation, based on some more involved integrability relation. That would be very interesting. And I will make this question more precise probably at the end of my talk. Okay, so first of all, I will introduce the problem, telling you how to solve this model, why the model is integrable, how to solve it with specific boundary conditions that are friendly to the computation of Feynman integrals, or certain Feynman integrals. And then, yes, how to formulate a general recipe to compute multi-point Feynman integrals with the topology of a fishnet. Okay. And then I may add some final remarks about how the procedure can be made easier to apply in some special kinematics. Well, let me recall you that multi-point Feynman integrals are extremely non-trivial quantities to compute. Here I will deal with finite multi-point Feynman integrals, but imagine a function of n points, where n can be 4, 5, 6, that live in 4 dimensions, so coordinates in 4-dimensional space-time. Let it choose to be Euclidean. And these are multiple integration with many loops and so on, right? So what type of functions describe these integrals is a highly non-trivial answer to which we don't know the answer. In general, are extremely difficult and non-computed quantities, almost never computed quantities beyond a few loops, so a few integrations, right? But let me be more concrete. So I will present things in this theory. This is just the theory that Volodya called B-scalar. He was calling fields phi1 and phi2. I will call x and z, right? But it's precisely the same. What is the main feature the main feature of this theory that makes it particular, easier, degenerate as you want, is that you have this type of vertex which doesn't coincide with its Hermitian conjugate, and that we study this theory at large n. Okay, so x and z are matrix scalar fields. We take n to be very large, and we consider only leading contributions. All right, leading contributions, together with this chirality condition, make the content in terms of Feynman integrals of the theory very, very simple. Okay, so any Feynman integral in the theory has the topology of a square lattice made of scalar propagators. Okay? In general, you have fields x that propagate from x to x bar, z from z to z bar, and this is the only structure that you can really get. The links, which would be, I think, if I think about the talk by Vladimir Bazhanov, this should be the link in the Ising type model in the analogy. These are just 1 over the square of the distance between the 2 points in 4D. So this square means x12 mu, x12 mu, right? Okay, so this is the model, right? It already looks like a lattice, so it already looks like this solid-on-solid model, but here everything, it lives in the 4-dimensional, in 4 dimensions. Now, in order to get something concrete for the theory, you can, so some concrete diagram, imagine this lattice to be infinite, you can draw a disk contour and cut these legs, and so set the white dots as fixed points, so as external points, and the black dots as integrated points, right? So these are the coordinate of this vertex, and so on are integrated, the external ones are not. Okay, so this means that such diagram will contribute to the perturbative expansion of this type of correlator, for example. And if all these fields are under the same trace, the same SUN trace, well, this will be the only Feynman diagram that contributes to the perturbative expansion, which is something very, very unusual. And it's due to the chirality. You can easily convince yourself that there is no Feynman diagram with a smaller number of vertices, of quartic vertices, that describes this quantity in the planar limit. You would need to add handles topologically, so go beyond the plane. Right? In particular, if we identify some of these external coordinates, for example, in the simplest possible way that we can think about while leaving the integral to be a finite quantity, that is in 4 points, okay, we get the object that Ivan explained for 1 hour. Okay? In this case, it's size 4 times 4, Basso-Dixon integral. Well, this Basso-Dixon integral is a very interesting object. Well, it is an integral which is computed at any loops, a 4-point integral computed at any loops, which is already very non-trivial thing, but it is in particular computable by means of integrability methods. Okay? So the integrability, as I will explain, delivers a result of this type. Now, let me recall from Ivan's talk what Z and Z bar are. Z and Z bar are...
Raise it a bit.
Shall I?
Yes. Otherwise people cannot see it.
Okay, I will raise it and de-raise it at the right time. Is it visible? So, these are usually defined in this way. If I have 4 points, these variables Z and Z bar parameterize these 2 ratios of distances, and these 2 ratios of distances are conformal invariant quantities. This type of diagrams are conformal invariants, are scale invariant quantities in the first place. And so one can always strip out of the expression of the diagram a standard factor that is just that doesn't get any. That is simply 3 levels, so it's a bunch of propagators. It's a bunch of square distances, and get. I mean, the pulp of the problem is to compute a function I mn of Z and Z bar. This is the real computation. So this is the real space-time dependence. The space-time dependence of the object is this. All the rest is trivial. So the point is that if you look at this expression now, there are no space-time integration. The space-time integration disappeared, and they were m times n, so a lot of space-time integration in 4 dimensions. Very, very complicated problem in principle. At the price of gaining m integration over the real axis in these variables ui, uj, so for I going from 1 to m, and m summation over the integers a. Right? Even more interestingly, n, I should say, n. Even more interestingly, everything is factorized in the different couples of UA, IA variables, which I will sometimes call excitation numbers or rapidity and spin, for example, because one is continuous and the other is discrete. And the only non-trivial, the only non-factorized contribution in these new variables is this measure delta ij, which almost looks like a van der Monde. Okay? So this is another signature of integrability. Well, long story short, as was showed by Ivan, this graph can be cast in as a determinant, where every element of the determinant m, as with some indices, is basically a ladder integral. So it's basically this function times a number that depends also on this. So m is f with the same index here, times a simple coefficient, simple number. So it is a determinant of this expression, of ladder integral, and which is an amazing result for a 4-point integral at any loop. Right? At any loop. So this result was, by the way, proved by, after having being derived via conjecture by Basso and Dixon. These results were proved by me and Sergei, based on separation of variables for a spin chain that I'm going to explain now, plus the procedure that allows you to go from this representation to the determinant representation, which was shown pedagogically in this other paper. Now, okay, Basso-Dixon was a small success for this kind of technique, but we should go well beyond this. We should take advantage of these tools to compute much more general object, right? So we can, let me limit myself to object with disk topology. So when I can get drawing a disk, carving a disk out of the lattice, for example, this, or even I can allow myself to puncture the disk, all right? Let me not go on cylinder or puncture sphere, as you want to, whatever you want to call it, like in this case. So let me live with open boundaries and never use cyclic boundaries. Why? Because otherwise I would get UV divergences whenever these wrappings go closer to the external points. This is a dangerous situation, and the methods we use is not really suitable for that. There are other integrability methods in order to deal with this problem. anomalous dimensions. Okay, so why is worth studying fishnet theory? It was already explained. There are many reasons you can find. For me and for this talk, it is interesting because we apply spin chain methods from integrability to the computation of multi-point Feynman integrals, and these multi-point Feynman integrals, they are not objects of interest of the fishnet theory, but for example, they can describe important quantities in n equal to 4 super Young Mills, which is a much more interesting theory from the point of view of high energy physics. And also in general, well, because in this theory we can compute non-trivial quantities, which will appear in general in QFT, such as these diagrams, and so we start shedding a bit of light on what is the space of function that could describe conformal correlation functions for multi-points. The object that, for example, were here in talks Volker and Jeremy. Okay, right.
Could you explain maybe the last point a bit more? What kind of dynamical regime do you have in mind?
Indeed. So, as I was showing you this object, which describes the Basso-Dixon in terms of the Basso-Dixon integral is the determinant of this object. These objects are what? Are ladder integrals. So these guys here are also fishnets, right? It's a minimal size, basically, of a fishnet. You have one propagator in one direction and many in another direction, where you identify the points in 4 points. Here I have z, 0, 1, infinity.
Okay.
Doesn't matter. I can explain it, why this. Right? Because if I parameterize the points in this way, I really have just a function of z and z bar without caring about that 3-level component part, but non-trivial part of the expression. Okay. So let's consider this expression. What is a dynamical regime? Dynamical regime is when I consider a correlator of 4 operators in n equal to 4 super Young Mills, which maybe here is not such a familiar theory, so I will be very rough. We have 4 scalar operators of a lot of fields, so L1, L2, L3, L4, which is the power of how many scalar fields enter this single trace operator, is very large. Okay? And this operator will be, in the conformal field theory, protected operators. So a specific class of theory that are called one-half BPS operators. Right? So in this regime, it is possible, remarkably, to solve exactly this object and write it as the Basso-Dixon integral, in this case as a linear combination of determinant of ladder integrals. And this, let me point out that it is a correlator, so it gets Feynman diagrams at every loop order. It's not just one single diagram. It's much more powerful result, but this theory is very special and it also has a lot of symmetries. Nevertheless, this is probably the only example I know of a non-trivial 4-point correlators in 4D QFT that it is computed at any loops.
Is it true for any L?
For any L?
L.
No, absolutely. It's a limit, indeed, where all the L should be very, very large. Otherwise, it is true, but only up to a certain perturbative order.
What kind of corrections there are, by the way? Is it the power in L or exponential?
The corrections are exponentially suppressed in L.
Mm-hmm. So it's like coupling to some power, like coupling to power L or something.
Right. Mm-hmm. Right.
And
Exactly.
the points x1, x2, x3, x4 are the fields that are evaluated at these points, or where are the points?
You mean y or x?
You have z and z bar refer to x's.
That's correct.
Yeah.
That's correct. So
Where are the x's?
right. They are the position of respectively these four fields. So
Okay.
in the full notation here will be trace of y, say 1 times phi in position x1 to the power L1.
Okay, thank you.
So where are the y's in the formula?
The y? In the final. I'm selecting a special projection. But the structure of this formula is valid pretty much in general.
You can write it for any choice of y's.
I would have to substitute, roughly speaking, I would have to substitute this factor with a factor which is a bit more complicated and includes also cross ratios in the y's and not only in the x. This is alpha and alpha bar. But I'm not sure now which paper wrote for the first time this formula with the generic so-called character, maybe by Didina Ivan and Valentina Petkova, maybe another one, so apologies. But yes, these are some of the people who worked hard on this problem.
Another question. It depends only on one cross ratio, only on the second one, is that right? I mean, if you multiply this 1 minus z times 1 minus z bar, you basically get this z plus z bar minus z bar. So it's just one cross ratio, right?
But there is no +1.
That is correct, but let me remind you that all these are ladder diagrams, right? So these are this F, you are defined.
Ah, okay.
All right. So these objects are important. You see that in this n equals to 4 correlator, basically the same building block is the Basso-Dixon integral. Okay, so in field theory we are interested in this type of objects, and if we look at them in the terms of field theory, they are indeed, as I explained you, the diagrams that characterize fully the perturbative expansion of single trace correlators. If I would consider something that I could call gauge symmetric correlator, so I have 4 different points and 4 different traces, well, then I should also care about the fact that around each puncture, so around each trace in this surface, there can be locally correction to the anomalous dimension of this external operator, which are a bit annoying to take into account with the spin chain formula. If they would give divergences, of course, UV divergences, that are not easy to normalize in this framework. So better to consider just what happens in the bulk, and therefore consider this type of correlators, if we want to give a meaning in Fishnet theory to these objects. Okay, so this is what happened in the bulk, right? A square lattice, which is basically a threefold, in this case, application of an integral kernel made of propagators, which you can call a transfer matrix. And in horizontal direction, you have propagation of field x, and in vertical or field z. What are x and z? Well, are fields that transform in a conformal theory. They transform according to a certain irreducible unitary representation of conformal group. They have a certain scaling dimension, which is 1. They don't receive quantum corrections. And they have a certain spin. They are scalar, so 0. S and S dot are left and right spin. Okay, we are in 4 dimensions. So we should use a certain spin chain model to relate this object to the transfer matrix of an integrable spin chain. And this object in analytic formula is written here. Okay? So you have distances between variable y's, distances between x and y, and here are just the boundary terms, as an integral operator applied to the function is a kernel that multiplies the function. Right? So let's look at the formalism that we use for doing these computations. So once again, I have certain representations. Here I will work with new real, so it's a so-called principal series representation. What I will need concretely is a bit of analytic continuation, because in order to get delta equals to 1 is analytic continuation respect the case new real, but it's all under control. What is the Baire propagator for the generic field in this representation is this kind of object. Right? Let me explain. So x squared is just the square distances to the power delta. And this bold x and x bar are the part that encode the rotation behavior, the behavior under rotation, space-time rotation of this propagator. Right? So you have sigma mu times x mu normalized and sigma bar mu times x mu normalized. Right? So if you take this object, this is the standard propagator for a Baire propagator of an object in this representation, and indeed under a conformal transformation that scales x and rotate also it, you will have this simple transformation law with the usual UMV that are the left and right rotations of spins. Okay, so for this object, I will always use this graphical notation. Right? You have an arrow because these are matrices due to sigma. Okay, also here we have a power L and L dot with the square bracket. What does it mean? It means that instead of this guy, I will use the symmetrized tensor product of L copies or L dot copies, such that I'm describing spin L over 2 representation. L over 2 and L dot over 2. So these are twice the spin, these numbers. Right, so I have a bar to denote where I have the bar, but the important thing is that there is a direction in these lines, because you go from dotted to undotted or undotted to dotted. So they are matrices. And this, and another fundamental notation I will use throughout my slides is the one for the fused SU2R matrix. Fused SU2R matrix in m, n fold representations, higher spin representations. Is a fusion, the standard fusion of SU2R matrix, and I will denote it when it is compressed between two so an x bar term and an x term. It just has a bar. You see? So here you have x bar, R matrix, and x. Okay, same distance, x12, but here is bar, and then multiplies their matrix, and then. This is notation I always use in this computation. So from now on, all the computation will be graphical. And this is why it's nice, because I use just star triangle relation, and otherwise they would be very cumbersome. Okay, so let's consider a spin chain where you have physical spaces and auxiliary spaces in this principal series representation. What is the solution of Yang-Baxter equation? Is this type of operator, which, as you see, is cumbersome. But if you use the notation I just explained to you, is four spinning propagators, simply four spinning propagators with two that have an insertion of an R matrix. The argument of the R matrix is related to the adjacent number, where these four numbers are the powers of the propagator, the scaling dimension of these propagators. Right? You see, U is a spectral parameter, and otherwise these powers depend on physical and auxiliary dimension, here space 1 and space 2. Okay, so how to spell the star triangle relation in the very general formulation, right? What I'm claiming is that this object solves Yang-Baxter equation, and therefore will be used to prove integrability of the chain we need in order to compute the graph. But really, as it was told by Vladimir Bajanov, the fundamental relation at the basis of integrability of these models is the star triangle relation. Okay? And indeed, here we could prove with Sergei, or at least recast with Sergei, some more or less known relation. We discovered that they could be interpreted and written in this way as a generalized star triangle relation, where I convolute three propagators, spinning propagators of the type I introduced, and I get a triangle with some factors, with some ratio of gammas, which is useless to spell explicitly now. Okay? So this is the analytic form, the operatorial form, where p's are I derivative, and x's are coordinates. Or if you want the integral form, also pretty cumbersome, but you see everything is really in this drawing. All the details are in this drawing. Okay, you read this drawing, you know these numbers, you see where is R, you can immediately. So computations we can do. And this star triangle relation implies all the relations that were mentioned, for example, in the talk by Bajan. Star-star relation, Yang-Baxter equation, and even more, in fact. Okay? The transfer matrix that one can build can even, of course, as usual, is a convolution of R matrices, of R operators. It enjoys factorization as the one mentioned by Bajanov, and in fact, one can also include some inhomogeneities, theta 1, theta 2, theta L, and have U1, U2, U3, UL, spectral parameters. Thanks to the fact that the R operator solves Yang-Baxter equation, one has immediately RTT, and similarly, there is an extra relation, which I call the TRT star, which involves the dagger of one of their matrices, and it is valid, in fact, under an extra constraint on the inhomogeneities, theta, which, by the way, I will not need in the case of the fishnet. And this is important for integrability, because you can claim that you have a family of commuting operators, but these operators should be diagonalizable, so they should be either Hermitian or normal operators Right? So otherwise you cannot diagonalize. So thanks to this TR T star, I have this relation that in particular implies the fact that the operators are normal operators. And they're certainly not Hermitian. Yeah, they are certainly not self-adjoint. Okay. So it's important. So actually, the claim of integrability of this model was, indeed I had to work this out, but it was substantially generalization to any spin and to inhomogeneous chain. That is, in every side of the chain, I in principle have different scaling dimension and spin. Based on the previous result that we had with Sergei Derkachov, or if you want, inspired from the two-dimensional result of Korchemsky, Manashov, Derkachov. Okay. So, in fact, the general Feynman diagram that you can diagonalize, since here we just identified that these pieces of graph as transfer matrices of an integrable model, looks like this. You can have any dimension flowing along these propagators as long as these vertices are all scale invariant and any spin that move around. So you have a generic vertex of this type, completely spinning. It involves 4 different spins, but it should, in order to be integrable, it should also have a very special matrix part in this vertex, which is given by 2R matrices. But since we are interested in providing a result to people who does QFT, let's look at some reductions on some specific choices of the representation in physical and auxiliary space. And for example, you can get the usual fishnet, which I want to compute, but also a lattice that forms this form of Yukawa vertices. So with fermions that will propagate, these are red. Red are fermions, and black are scalar propagators. So fermions that propagate in one direction, or fermions that propagate horizontally and scalars in other direction, or mixed situation with the fishnet and, say, honeycomb lattice of Yukawa vertices, and so on. So let's go back to our example. So far I spoke about the transfer matrix, which is trace of monodromy matrix, so I'm imposing boundary conditions which are cyclic. It's still not the object we have in the Basso-Dixon integral, which has fixed boundaries. Okay? Open boundaries if you want, but let's call them more properly fixed boundaries. Okay? Well, how to do then? I proved integrability for this model. I will prove that if I insert a twist in the transfer matrix that opens my boundary, the twist is doesn't spoil integrability. And this is what one can do. Okay, so the new transfer matrix I will call Q. It will have L sides. It will be characterized by a certain choice of a representation in auxiliary space A. So it's still, if you look at this line, it's still a product of our matrices, which I have here in the drawing. But now you don't identify first point with last point. You rather integrate the first point and fix the first point is integrated and the last point is fixed to external coordinate. Okay? Technically, this is realized inserting a certain twist, which I call gamma x0, x0, in the trace that defines a transfer matrices, and you can check simple invariance properties respect to their matrix such that the two relations that allows to claim integrability are respected. But in fact, we don't really need to argue integrability at the theoretical level, say, when we can really diagonalize the chain explicitly. So I will now build the eigenfunctions of the chain and diagonalize it explicitly. In fact, if my chain has only one side, it's almost obvious to diagonalize it with a function that have a certain scaling behavior, basically parameterized by quantum number nu, okay? And a certain rotation behavior under rotations. You can replace, in fact, this numerator by a Gegenbauer polynomial or a spherical harmonics, say a spherical harmonics in 4 dimensions. Zonal spherical harmonics even better, because the problem is a rotational symmetry. You don't need magnetic angular momentums. Yeah, this is very simple to realize that for only one side, you don't need integrability after all when you have one side. But what is remarkable is that for a spin chain with k side, we are able to find a function, or rather an operator, that satisfies this separation of variable conditions. Say, This operator carries quantum number y, which is mu and n in general, y mu and n. And it's exchanged with the transfer matrix, deleting one side, so giving a chain which has one side less. It is invariant, it is not changed, the lambda operator, and it spits out a factor. Okay? So if you iterate this relation until k becomes 0, you have diagonalized the initial operator. Right? Because every time the spin chain is reduced by one side, in the last step you know how to diagonalize. Because you have this eigenfunction and the problem is solved.
Sorry guys, can I ask, so for the operator which you are diagonalizing, can you formulate it a bit more algebraically? So is it right to think that it's the transfer matrix where both physical and auxiliary space are in principal series representation?
That's correct. Or complementary series. Irreducible unitary representation of the conformal group. All right. So how does it look, this lambda or layer operator? Okay? When you have length 3, for example, it is made like this. You have one triangle, one other triangle, and then this is just one propagator, which is the length 1 eigenfunction. Here delta 1, delta 2, and delta 3 are the representations in the physical spaces, side 1, side 2, and side 3. Nu, which propagates, as you see in this direction, nu minus nu, is the rapidity of the excitation, which is carried by this operator, and this dashed line, as usually, represents a spinning numerator, so the rotational part in the numerator of this type, and it carries also the index n, which is the spin representation. So due to this iterative structure of the eigenfunction, you just have to convolute the layer of length L minus 1, up to layer of length 1 with some normalization, which is unimportant. For example, layer of length 4, layer of length 3, and so on. You will build a pyramid, and this pyramid will diagonalize the transfer matrix. So we'll diagonalize when delta 1, delta 2, delta 3 here, for example, and delta 4 are equal to 1, the Fishnet graph.
So algebraically speaking, normally when you have separation of variables, the wave function factorizes into Q functions. But here it factorizes into some very fixed functions that you don't need any Baxter equation or anything. They are kind of completely fixed from the beginning. So is it because you are diagonalizing in a way some simpler operator than normally?
Simpler, it is simpler to diagonalize for certain because of the open boundary conditions.
Yeah, because this is open. Yeah, so
Fixed
roughly
boundary
speaking, it is like one element of the monodromy matrix instead of the trace in some sense, right? Something like the A operator rather than A plus D in a way.
You can do this type of identification when you have SL2C spin chain.
Yes.
We don't know such an analog in 4 dimensions.
You even don't know the. I see.
No,
so you
I
don't know the
wrote
link
explicit.
The link to the monodromy matrix with finite dimensional auxiliary space.
Exactly.
You don't really.
Exactly. Okay, so this eigenfunction also enjoy very interesting, very nice properties. That is, are symmetric if I exchange two quantum numbers. That is, if I take two of these layer operators with excitation y and y prime, modulo a change of normalization, modulo a factor, which is not much important, and a rotation of the spin degrees of freedom by fused R matrix on the left and on the right, they just switch the excitation. So y prime becomes y prime 1, y, time the multiplication of by the R matrix. Okay. Which is basically this relation is a bit small to read, but this was showed on the right. And also, in order to compute the scalar products, we found a remarkable relation. So if you take lambda dagger, which here I call lambda bar, and lambda, and you collapse them, so you overlap them, they become exactly the same operator with one site less. So once again with this iterative procedure of reducing one site at each passage, times once again a certain factor, R matrix on the left and R matrix on the right. Now, here you notice that for the first time there is, beside the R matrix, something that depends on, in a non-factorizable way, on y and y bar, right? So as I showed you before in the Basso-Dixon integral, the only non-factorized thing in the integrability representation of the Basso-Dixon integral was indeed the measure, right? Here we are computing under Dagger lambda, so a scalar product, and we are finding the measure, right? So this mu is a modified Vandermonde, basically.
Why you have so, you would expect to have more quantum numbers parameterizing your representations.
Sorry?
The generic representation of this conformal group. You have 3 quantum numbers, the three Cartan generators.
Yeah. Exactly. Delta, S, and S dot. In each side.
Why you have only 2 parameters here? What happened to the third parameter?
Yes, so the excitations have only rapidity and 1 spin.
Because you have chosen scalar operators. No?
No.
No, general representation. If you're constructing R matrix, which acts on the tensor product of representation of conformal group.
But these are our matrix acts on auxiliary or physical space. Here are these numbers are the quantum numbers of the eigenfunction. I'm not saying that. So of course they have a conformal behavior, but these are not the numbers of the physical or auxiliary space.
There's a quantum numbers nu and n. The quantum numbers of a particular representation of conformal group.
Yes.
My question is, where is the third number? Why?
Because if you diagonalize a hydrogen atom, okay, which has a rotational symmetry, how many quantum numbers? There is rotational symmetry. That's my answer. I mean, if you want to diagonalize a problem with central symmetry, then you need power law behavior, 1 over R to something, and the rotational part. But if you have rotational symmetry, you don't need the magnetic quantum numbers, right? You just need the J, you don't need J3, and so on.
No, I don't understand. Let's talk about something which we agree upon. You have quantum fields transformed according to the representation of the Lorentz group. Mm-hmm. This representation parameterized by 2 Lorentz spin. Let's say n and dot. You have two subgroups. Each of them gives you difference between n and dot, the spin of the particle.
Well, maybe you want to ask where are the indices? Both the indices in this representation. Okay. So if you look at the eigenfunction for length 1, this is x minus x naught contracted with the sigma matrix. On the right I have dotted, on the left I have undotted.
This means that you have chosen from the very beginning, from the set representation, which have n equal n dot.
N, yes, and
therefore you're talking about spinless. The difference between the two is spin of particle.
Okay. Mm-hmm.
So you're talking about spinless particle.
Right.
Why?
Well, I never think about this as particles, but okay, yes. This is usually called bound state index, but it has a rotational behavior, right? Because it is in a certain representation of the symmetric higher spin representation. But as a particle, maybe you can say so. Nevertheless, when you scatter 2 of these excitations, they scatter via inner matrix.
Yeah, but this means that if you start from the very beginning, so there is some selection rules which tells you that if you start from the scalar, I don't know, if you start from the scalar particles, if you look for all possible channels, most likely you will never get, let's say, particles which cause pheromones probably will never appear.
No, you have to have the full system of eigenfunctions in this story. Probably it's like in spherical harmonics, you simply drop the dependence on phi angle because it's trivial, and you have
I don't know.
Probably it should be
This function you can call, this is basically so-called zonal spherical harmonics, right? When you already summed up in the eigenspace of n.
You don't agree that if it is x minus x dot power n, it has even number of dotted indices, equal number of dotted and undotted indices, simply because of the backconstruction.
Absolutely. Yes. Yes.
So which means that you're talking about this lambda belonging to certain representation of Lorentz group, which n equal n dot.
That's correct. Yes.
My question is, I want to look for the solution to the Baxter equation, such as that this balance is violated. So number of dotted and undotted indices is different from 0. Like take fermion I want to construct aromatics for scattering of fermions, which are, let's say, spinors with one index.
I think one should formulate the problem. So what I showed before was an R matrix with really 4 spins. So dotted and dotted, dotted and dotted, but also 2 rapidities, two deltas. And this is completely general. Now when I look at excitations, the R matrix that shows up here is just that one which is spin structure. And I mean, it is a SU2 R matrix, so it can act on 2 spaces. One spin and another spin, right? So if I scatter 2 excitation, every excitation can contribute only with 1 spin. So this is what I see. I don't know if it is possible to realize something where this line, which probably was it, is doubled. Okay, so I have one line which has spin n, and one line I change dotted and undotted, and it is n prime or n dot. I wouldn't have this under control. I wouldn't know what is the star triangle relation for that and what this is for, by the way.
So that means that your system of the functions is not complete.
No, my system of function is complete.
Okay.
Actually,
yeah, I propose that
so I do one last statement. I think that maybe from a philosophical point of view, the resolution of your question stands in the fact that our matrix factorizes. Because also in auxiliary space, you can have 2 spins. But if you factorize the R matrix, 1 spin is in the first factor and 1 spin goes in the second factor. And both are enough your integrable system could be defined equivalently only by first half or by second half. So that's a bit hand-waving, but no. All right, so now we will speed up. It's not true anymore that I will finish before. So
how much time do you need?
how much time do I have?
Well, 5 minutes in principle.
It's okay. 10 minutes maybe.
Yeah.
Now you're eating 1 minute, that's really laughing. Okay. So the answer to question by Volodia is that we have orthogonality and completeness. Completeness is conjectural beyond length 2, but it's just because you should see it and make very cumbersome computation, but it will work. And so you can write a transform where you go from space of coordinates, space of excitation. As usual, you pair eigenfunction with the generic function, and you can transform back going from space to excitation or space of coordinates, right? So you can insert a resolution of identity, summing over prime ket of these eigenfunctions, and what? You will diagonalize a portion of fishnet that stands on the left and on the right. So this is what I want to do. I have a fishnet. I don't want to compute integrations by any trick of quantum field theory, but I want to get rid of the integration, of the loop integration in coordinate space, paying the same price for for any size of the fishnet. So I can have a lot of lines here, but I pay the price only once. That is insertion of 1 basis. Okay? Because how many operator I have will be just the power of the eigenvector, since that is just how many transfer matrices I have one after that. So for example, let's take this situation. Depending on which boundary condition I set, I can obtain Basso-Dixon configuration, 6-point configuration of this type, 7-point configuration of this type, or even more complicated cases where I have a puncture in this, but the point is that I always have to cut, that is, insert a resolution of identity of this basis along these vertical lines, and see therefore a spin chain with 2 sides, 2 sides, 2 sides. In all the situation, I could have a spin chain with 3 sides, and so on. Right? So I have, for example, with 3 sides in this situation, and I insert the resolution of identity, factorizing a part of the diagrams, and concretely doing a triangulation of every fishnet integral. Now, since this portion of fishnet gets factorized, that is, I touch my eigenfunction, first layer passes through and produces some eigenvalue, second layer passes through and produces second eigenvalue, third layer here passes through, and I go back to my eigenfunction producing eigenvalue, and I have no Riemann diagram anymore. Okay? So at this point, I'm just left with this picture. Feynman diagram disappeared. I just have bracket, 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 bracket. And now I have to collide them just to compute some overlap of bracket eigenfunctions, but relative to different spin chains. That is, spin chains, for example, this and this, they have indeed different boundary conditions. These 2 points and these 2 points. Okay. In fact, the most general situation is, which can appear, and is most non-trivial to compute, is when I have to compute overlap of 3 functions. Right? For example, in the case that I would have a propagator in this direction, a propagator that is absorbed by external point, and a propagator that continues across this other cut. Well, for example, here I would have to overlap 3 eigenfunctions from 3 different spin chains. Okay? But that non-trivial spinning version of the star triangle relation, and only with that, you can compute this object. So since now I have probably 2.5 minutes, I will show a movie of this diagonalization. Okay. Every time I put some light on a portion of this diagram means that I am applying a star triangle. I am not writing, of course, of the spinning structure or their matrix. Right? You recognize that all the dashed lines here have been dropped for your comprehension, for the sake of your comprehension. Okay, so let's go. Okay, so first, this is the starting situation. I apply star triangle at these 2 points. And then I get this, and then I can apply star-star relation here, and then I can apply star triangle, and again I can apply a star triangle again here. Here you can imagine there is a leg to infinity. This is a simplified star triangle. I get this. So I get rid of all the space-time integration. I can compute this. I start from a many loop, many point Feynman integral. I get quantities where the space-time integrations are completely gone. Okay. And I have a product of, this would be x3, of course. I have a product of propagators with spinning numerator and with some matrices in the numerator. How do they look? Oops. Okay. Well, they look like this. All right? More specifically, let's take. Okay. This is the situation. Now, inside the diagram, I will have at this point, since diagram disappeared, I know how to diagonalize it, and I know how to overlap the functions. Now I have to take all the triangles of the triangulation and put them together. And at this point, I will be back to the full expression in the basis I propose. So let me take 2 of these triangles in a specific example. So I have 1 cut, which crosses 2 propagators, so I have 2 excitations, yn1 and yn2. Here I have only 1 propagator, so 1 excitation, spin chain of length 1. Here I have also spin chain of length 1. And here I have also spin chain of length 1. Right? I have to compute the overlap between 3 eigenfunctions, one with yr, one with ym, and one with yn2, yn, and 1. And an overlap in the second triangle with yn1, yn2, and bra, ys. And in this cut, there is no propagator going, so I don't have to cut or glue anything. I don't have to insert any resolution of identity. This is my last slide. Well, okay, so I showed how to compute with the movie. Here is a bit more detailed. I'm keeping track of the numerator, of this propagator and the spinning structure, of where our matrices, fused SU2 matrices enter. But it's very easy. You can, all this computation you do by hands. And every time you apply a star triangle, you just take into account the scalar factor that star triangle produces. Okay? At the end, you put everything together and you get certain contribution. H here, and this contribution is factorized in every couple of excitation, which is the signature of integrability once again. So it's factorized in this type of function that every time involve only 1 excitation from 1 cut and another excitation on from another cut with whom that they interact, so cut common to the same triangle. And when you glue the 2 triangles that have 1 cut in common, what you get? You get this. You get this. But then let's consider the contribution of every excitation to the representation of this integral. So let's drop everything which is not from the basis that was inserted along this cut. For example, you get this simple expression, a square of propagators, that you organize in a cross ratio times the rapidity and the spinning structure with certain SUN matrix. That can be actually a bit more simplified. And then you can repeat the same the same thing, so the same contribution will be from all the other squares. So for all the other bases inserted along the other cuts. I choose cut 1, 2, and I get this square. In cut 2, 3, I will have this purple here and another half, another square, and so on. So finally, each excitation gives a weight factor, so a coordinate dependence factor of this type. Okay. Coordinate dependence factor of this type, which I call W. Eigenvalue, which is produced by diagonalizing the fishnet, so the content, the fact that there was a fishnet to diagonalize is all here, if there were L application of the transfer matrix, so L, size L of the fishnet. This factor that coupled to other excitation in the same triangle, and this is the measure, is just another way to express this mu measure, which looks like a Vandermonde. Okay. And this reproduces basically a conjecture based on ADS-CFT integrability, true for n equals to 4 theory, pushed to the fishnet limit of strong deformation of n equals to 4 that Volodya explained to you. So it is in few words, is a nice test of the conjecture that was made for n equals to 4 in the fishnet limit. So another example, beside the one that Volodya cited of the spectrum, where fishnet theory can, where the integrability of a conformal field theory arises directly from Feynman integrals. Okay. So thank you for your attention. Is it wrong? Is it wrong? It's correct?
No, slide error. There should be a space before the exclamation mark.
Space for exclamation mark. Why?
Because it consists of two
I see.
isolated components. Very important.
Time for one quick question. So if the questions are exhausted, let's thank Enrico again.